Hello. So this should be part 2 of the series. I think trying to optimize things. The last video things weren't exactly central, and got to get my microphone a better spot for better sound. But you know what? First YouTube video. It's normal, guys. Totally normal. Anyway, what we'd like to do here is optimize the circuit a bit. Now, there are two ways we can re-trigger the power coming back. The one is just to simply wait for the battery to charge up sufficiently and switch back on based on the battery voltage. The other way to do it is basically put a monitor in the main side. Easiest way is probably just to have a diode and just detect when the mains voltage comes back. Obviously, mains voltage after transformer, so that you can see that the power's back on, and then you know the battery will be charging, so you can switch the load back on at that point. There are pros and cons of those two methods of doing things. The pro for the power coming back is it'll be pretty immediate. You don't have to wait for the battery to recover. The con is, of course, if your charging circuit fails in some way, which I suppose, or the diode, mainly the diode fails, then you would never switch back on. So I'm just going to run through the second method, which is possibly not going to be my final solution, because detecting the mains coming back actually seems more reasonable to me. I should pick up a Schottky diode so that the voltage drop isn't too great when we're charging the battery and running CPE and a router. In any case, just for the sake of completeness and how things work, let's build out a basically it's almost the same circuit as this again, except output of the op-amp will go onto our switch. The switch, of course, being what will reset the circuit after it latches off. So I'm just let's monitor the voltage here. 13.8, so I'm just going to drop 0.08. Just drop it down until it shuts down. This should be the same as our previous video. And did it flicker there? I have to check the footage. That's odd. We're now below shutdown threshold. Got 9 volt. 9 volts, yeah. When I pulled that capacitor out, I might have, and yes I did. Okay. The reference supply went for a walk, basically. And just shorten that reference. Yeah. Okay, great. Let's go back up to say. Nice thing about doing this is you can hook it in. Let's go back up, reset it, and drop back down. 10.6, 10.7, and then latches off, and we can come back up. So that behaving as expected, basically where we left off last time. Now the op-amp output is probably indeterminate, but let's just see what happens. So the op-amp is probably outputting so. So what we want to do is almost exactly the same circuit as last time. And by the way, these circuits are fairly standard, fairly consistent. Basically, it's a level detector. You're just detecting a level voltage against a known reference voltage. So, it's nothing too complicated, and although I have used the link in the description, I'm just setting up another reference, this time without a transistor, because it doesn't need to latch with the transistor. So that should give us same 4.7 volt Zener, same 1.5k resistor, and that gives us nothing. Have I? Brown, green, red. It's a bit odd. 10.5 volts. Got the diode the wrong way around. Shouldn't have. Shouldn't matter if I do. It's not like it's high current or anything. The resistor protects us. It's all nothing. So this diode may be pulling us down. This diode might have faulty out of the box. Let's bring in the slightly dodgy machine. Pin 1 to pin 2. It's actually a rather nice circuit holder. Okay, we have a faulty Zener. Bear with me while I get another one. That's a bit odd. We have more. These things happen, guys. Okay. Zener diode. Wait, again, yeah, that should be the right way around. Let's turn off this. 4.4. 4.4. So what we can do is, and I prepared these earlier because I sort of know exactly what I'm going to do. I'm not sure where it's going to come back. If it works the wrong way round, we can always just swap them in and out. That way we don't have to think too far. So that's our reference for one side of the op-amp. I know one of those pins is negative and the other one's positive. Not entirely sure which at this point. But, okay. We'll have a setup exactly the same as before. I'm just going to short one side of this together. So basically I'm shorting the center pin to the one end pin and the other pin to ground. Just a fairly standard way of doing that. And then the third pin can go to positive rail via a 22k resistor. So essentially it's the same circuit as before, and this will give us, depending on what the plot is set at, 8 volt reference. Now I'm going to switch on voltage, which I'm going to set to 11 volts, yeah? See? 11.1, close enough. Let's go down a bit. 11 volts. We want the reference voltage to be comparable to the measure voltage to be comparable to the reference voltage. So we're aiming for about 4.5. So I'm just going to slide this on in here and do some adjustments. It's going up, we're going to go down to around about 4.44. There will be some offset on the op-amp, so don't have to be so exact. And might have to tune this a bit once it's in use. So what we can do is we're going to connect our reference to our other pin on op-amp. May or may not have got it right. So we dropped the voltage. You guys didn't see that, but we did. And the light goes out. So I'm just going to plug this meter in for reference. And actually, perhaps I should move it across here. No, it's not as visible, I think. That's possibly our best bet. Our arbitrarily sized capacitor from last time. Let's stick it there for now. Okay, so 10.5, we're off. Come back on immediately. Shouldn't happen, so what I'm going to do is swap around the pins. Go off, and we don't come back on. This is important. So, your power drops down, your battery voltage drops down to 10.5 during the power failure, and you disconnect your load, the battery voltage rises as lead acid batteries do, but it doesn't turn back on until you've got mains back, hopefully. So we can go up in the voltage, and it re-triggers about 11.1 volts. So that's nice and easy. I should perhaps doodle the circuit out for you that I've just built. So give me a moment, I'll get something to write on. Okay, and we're back. So essentially I'm going to doodle half the circuit. We've got our op-amp. Yeah, something like that. It's our out. And this will go to the via 10K to the base of our transistor. And that then we'll have the Zener, draw some sort of Zener, move this a bit more up, and then you've got your 1.5K. Maybe we need to, and that's your positive rail. And that goes to the other op-amp, rest of the circuit there. We're not worried about that. You can look it up on the link if you need. So then we've got our positive and our negative. And what we've got here, so we've got our 1.5K. Yeah. And then we've got our Zener, there, something like that, to our ground. Can't draw a ground apparently. And then we've got our 22K, and we've got our in this case, it's a 20K resistor. So, what this means is we've got pin 5, which is our non-inverting input, is connected to our reference. And our inverting input is connected to our, not our reference, our measurement. So all that happens is when our measurement drops, when our measurement increases above our reference, the output will go on, and we'll switch on this transistor and allow the low voltage cutout to unlatch. Nice and easy. If you want, for completeness, we can draw the power rails. And, that's what pin 8 and pin 4. And this would be pin 5, no, pin 6 and pin 5, and this will be pin 7. So, not a particularly complicated circuit, and it works. Now, it's possibly a bit overkill, because there's another way of doing this. And that is, let me doodle this out. We have this point here, which is our switch point. And what you'll do is you'll have a battery charger of some description. I'm planning to use another little board and a sort of wall power supply. So this is your positive in battery. And if you stick a diode here, I recommend a Schottky diode because low voltage drop, not much heat dissipation is required. Excuse me while I cough. Got a bit of cough that won't go away. Anyway. And then this will come to your battery. Your lead acid cell, 12 volt cell, sealed lead acid. And this is your negative from your battery charger. And this goes off to our battery protection circuit. Now, when the mains is off, the battery charger will stop working. So you will find that this point remains at battery voltage, and this point here will basically drop to 0 volts. So when the power comes back, this point will come back up, current will flow, charge the battery, run your circuit. If we connect this 10K switching point directly to a point here, what will happen is the moment the power comes back, the circuit will latch reset. That doesn't mean the load will come back on. You must still go above your minimum set point from the other circuit. But it does mean that we know there's power. The only disadvantage is, in fact there's no real disadvantage, because even if the diode fails and explodes, your meter doesn't like remain on. Your minimum set point is still in force. So even if, I'm just going to remove that and connect it to the reset. That's connecting this point back up to this rail, yeah. What you'll find happens is the load remains off, as you can see by the LED, until you increase the voltage, and let's bring the meter back in, until you increase the voltage. So it's just going to stop the battery discharging any further than your set point there. So it comes back on. If you want to do it that way, that's quite reasonable. So is this method. This method will possibly be a little bit better for your power supply because it won't have to charge the battery from flat and run your load at the same time. But practically speaking, we want to choose a big enough power supply on this end that we maybe 3 amps something, that we don't have to worry too much about that. Okay, 2 amps might do it. Let's go back to this. We'll shut it down, and it doesn't come back on until we get to our reset set point. So these are two options of auto recovery. The push button seems to me to be, and no offense to the gentleman who designed the circuit, it is very well designed, and he's done me the favor of working out all the, all the currents and stuff, what's required to drive the MOSFET, etc., etc. There's possibly room for optimization there, but there's also possibly no point in it. Okay, so that is a low voltage battery cutout and restore circuit. What we might do just for fun is connect up one of these and simulate the circuit, and just watch what happens to the output, how quickly it drops away and so forth. I'm probably going to have to solder this. Probably solder some jumper cables on. I've got a pile of them here. Yeah, so that will fit through there just fine. And we can just run a bit of solder over it, make a good connection. Plus I've connected a black wire. Lovely. And then we can actually plug it into the board, and we can potentially on output connect I've got a little electronic load, designed mainly for USB, but they operate at higher voltages too. And we can see how just by feeling it, I don't have a thermometer at this point, we can see how well the diode does. I mean the MOSFET does. Does it get nice and toasty, or does it remain calm? So I'm just going to go off screen and pause you guys for a moment while I go and fire up my soldering line.